Hey everyone, and welcome back to the channel. Ever faced a problem or maybe read about a scientific discovery and found there were multiple ways to explain it? How do we choose? There's a popular idea. The simplest explanation is usually the best. You might have heard it called Occam's razor. But what exactly is Occam's razor? It's a principle that suggests, when faced with competing hypotheses, the one with the fewest assumptions should be selected. Named after the medieval philosopher William of Occam, this idea has been a cornerstone in scientific thinking for centuries. It's not just about simplicity for simplicity's sake, but about finding the most efficient path to the truth. So how does this principle apply in real-world scenarios? Let's dive deeper and explore its significance. It sounds appealing, right? Keep things simple. Our brains often like elegance and dislike clutter, but just saying simpler is better can be misleading and doesn't capture the real power or the limitations of this idea in science and critical thinking. So today, let's sharpen our understanding of Occam's razor. What is it really? Why is it useful? And when should we be cautious about applying it? At its heart, Occam's razor isn't about picking the explanation that's easiest to understand. It's a principle of parsimony or economy. This means that when faced with competing hypotheses, the one with the fewest assumptions should be selected. This principle has been a guiding light in scientific inquiry, helping to strip away unnecessary complexities and focus on what truly matters. Imagine you have two theories, Theory A and Theory B. Both perfectly explain all the data you currently have. Occam's razor suggests you should provisionally prefer the theory that makes fewer unnecessary assumptions or posits fewer unnecessary entities or processes. Entities must not be multiplied beyond necessity. This idea is famously linked to William of Occam, a 14th century English philosopher and logician. While he might not have written that exact Latin phrase, it captures his approach. The razor metaphor suggests shaving off those extra, unproven assumptions. This principle has been a guiding light in scientific inquiry, encouraging scientists to seek the simplest explanations that fit the evidence. From the mysteries of the cosmos to the intricacies of quantum mechanics, Occam's razor remains a powerful tool in the quest for knowledge. Crucially, Occam's razor is not a law of nature saying the universe must be simple. It's a heuristic, a practical rule of thumb, a guide for thinking, especially when evidence alone doesn't point clearly to one answer. It doesn't guarantee truth, but it helps guide the process of inquiry. So, why is this preference for fewer unnecessary assumptions so valued in science? It helps in creating models that are easier to test and validate, leading to more robust and reliable scientific theories. First, fewer assumptions mean fewer potential points of failure. Every assumption you add that isn't backed by solid evidence is another way your explanation could be wrong. A simpler theory in this sense is often more robust. Second, and critically for science, simplicity often equals testability. Theories with fewer moving parts usually make clearer, more specific predictions. This makes it easier to design experiments to try and disprove them, a core part of the scientific method known as falsifiability. Complex theories with lots of adjustable bits can sometimes be tweaked endlessly to fit any data, avoiding real scrutiny. Occam's razor pushes against these ad hoc rescues. Third, simplicity aids in communication and understanding. Simple theories are easier to explain, teach, and understand. This accessibility can lead to broader acceptance and application. Complex theories, while sometimes necessary, can be barriers to wider comprehension. Occam's razor encourages us to seek the simplest path to understanding without unnecessary complications. Third, simpler models often generalize better. They're more likely to capture the essential underlying pattern rather than just fitting the noise in one specific data set. This improves predictive power. Finally, there are pragmatic benefits. Simpler theories can be easier to work with, understand, and communicate. While ease doesn't equal truth, it helps in building and sharing knowledge. Moreover, these theories often require fewer resources to test and validate, making them more practical in real-world applications. Let's look at some examples. In medicine, you've probably heard the saying, when you hear hoofbeats, think horses, not zebras. This means that doctors should first consider the most common and likely diagnoses before exploring rare conditions. If a patient presents with common symptoms, doctors are trained to consider common diagnoses first, the horses, before jumping to rare diseases, the zebras, even if the symptoms could theoretically fit both. Why? Because common diseases are statistically far more likely. It's about diagnostic efficiency. Start with the simplest, most probable explanation that fits the symptoms. Of course, doctors also know Hickam's Dictum patients can have multiple problems at once, so blindly applying the razor can be dangerous if it stops them looking further when needed. It's a balance. In the history of science, think about the shift from Ptolemy's Earth-centered model of the cosmos to Copernicus's sun-centered model. Ptolemy's model worked. It predicted planetary positions reasonably well for centuries. But to do so, it needed a complex system of circles upon circles, like epicycles, deferents, and equants, tailored for each planet. Copernicus, on the other hand, placed the sun at the center. This conceptually simplified things dramatically. For instance, the confusing retrograde motion of planets became a natural consequence of Earth overtaking outer planets, or being overtaken by inner ones rather than needing special epicycles. Now, nuance is key here. Copernicus's initial model, still using perfect circles, wasn't necessarily simpler to calculate with and wasn't immediately more accurate. But its fundamental structure was seen as more parsimonious. It explained more with fewer core types of ad hoc mechanisms. It had greater explanatory coherence, which appealed to the principle of parsimony. Its eventual success came with later refinements like Kepler's ellipses and supporting evidence. Everyday logic. The hoofbeats example works here too. If you're in the UK like me, or the US and hear hoofbeats outside, assuming it's horses requires fewer unusual assumptions than assuming escaped zebras. The simplest explanation here is deeply tied to context and background probability. Change the context to the African savanna and the parsimonious assumption shifts. In science, Occam's razor is a guiding principle. It suggests that when faced with competing hypotheses, the one with the fewest assumptions should be selected. This doesn't mean the simplest explanation is always correct, but it's a useful heuristic to guide our thinking and research. By applying Occam's razor, we can navigate complex problems more efficiently and avoid unnecessary complications. Okay, Occam's razor is useful, but it's not a magic wand. We need to be aware of its limits. Most importantly, evidence trumps simplicity. If data clearly supports a more complex theory, science accepts the complexity. The razor is for choosing between theories that equally explain the current facts. It guides, but evidence decides. Super rule number 1, empirical evidence overrides parsimony on screen text. Rule number 1. In the end, the simplest explanation is preferred only when all other factors are equal. But when evidence points to a more complex reality, science follows the evidence. Occam's razor is a tool, not a rule. It helps us navigate the complexities of the natural world. But ultimately, evidence is the final arbiter. Complexity isn't forbidden if it's necessary. Remember, entities must not be multiplied beyond necessity. Science embraces complexity when reality demands it. Einstein is paraphrased as saying things should be as simple as possible, but no simpler. Simplicity itself can be tricky. Are we talking fewer entities, ontological simplicity, or simpler equations, syntactic simplicity? These don't always align. Judging simplicity isn't always clear-cut. The challenge lies in balancing these aspects to find the most effective explanation. And beware of oversimplification. Applying the razor too aggressively, especially in complex fields like biology, as Francis Crick warned, or social sciences, can lead to missing crucial details or interactions. Let's quickly bust some common myths about Occam's razor. One common misconception is that it always favors the simplest explanation. In reality, it suggests the simplest explanation that fits the data. Another myth is that it's a rule of thumb rather than a definitive principle. However, it's a valuable heuristic in scientific modeling and theory selection. Myth 1. The simplest explanation is always true. Reality? Nope, it's a preference guide among equally fitting theories, not a truth detector. Simple ideas can be wrong. Myth 2. Simplicity is the most important factor. Reality, empirical adequacy, fitting the facts comes first. Simplicity is often a tiebreaker or starting point. Myth 3. Occam's razor is a rule of thumb. Reality, it's a heuristic, a guiding principle, not an absolute law. Myth 3. Simple means easy to understand or familiar. In reality, it refers to technical simplicity, fewer unnecessary assumptions or components, not necessarily conceptual ease. Quantum mechanics is complex to grasp, but arguably parsimonious in its fundamental postulates. Myth 4. Always ignore the beyond necessity part. Reality, the razor targets unnecessary complexity. Complexity required by evidence is fine. Occam's razor is not about oversimplifying, it's about finding the simplest explanation that still accounts for all the evidence. This principle has guided scientific inquiry for centuries, from the time of William of Occam to modern-day research. So, Occam's razor, the principle of parsimony, remains a valuable tool in our thinking toolkit. It encourages us to favor explanations that are economical with assumptions, easier to test, and less likely to be burdened by superfluous additions, provided they fit the evidence. It's not about finding the easiest answer, but about promoting a rational, structured approach to inquiry. It pushes us towards explanations grounded in evidence and logic, demanding justification for added complexity. Think of it as a form of intellectual discipline, forcing us to ask, is this assumption really necessary? It helps navigate uncertainty, guiding us towards potentially fruitful paths while reminding us to be cautious about unnecessary speculation. It's one important principle, among others, for clear, critical, and scientific thinking. What are your thoughts on Occam's razor? Have you seen it used well or misused? Let me know in the comments below. And don't forget to like, share, and subscribe for more intriguing content. Thanks for watching. If you found this useful, please give the video a like, subscribe for more content on science and critical thinking, and hit that notification bell so you don't miss the next one. Thanks for watching, and keep thinking critically.